Welcome to section 3, training a supervised learning model. This is lecture 9, improving the logistic regression model through hyperparameter selection. So to kick off where we were last time, we trained a simple logistic regression model. We evaluated the effectiveness of that model on the test set, made predictions on the test set, and we produced a confusion matrix to see how well the model fared in terms of detecting fraudulent cases and how many false positives, etc. it determined. So that was a baseline solution. This second implementation that I've coded up in my cell includes one hyperparameter, which is the class weight. And hyperparameters are things that you could tune on the model itself. So you can think of them as knobs or buttons that you can tune in relation to one another to help the model generalize better, to help the model train better, to reduce overfitting. There's different hyperparameters. Every model has its own unique set of hyperparameters, or algorithm has its own set of hyperparameters. And in the imbalanced class issue, typically balancing out the class weights is one of the most important hyperparameters I found. So with the logistic regression implementation in scikit-learn, it makes sense to pay attention to that hyperparameter. I mean, there are hyperparameters that you can implement to reduce overfitting as well, but in this case, what we want to focus on first is just paying attention to the minority class first. So what this effectively does is it balances out how the model gets penalized at training time. So it's effectively telling the model, pay attention to the minority class in more detail, but it's doing that automatically by balancing out how the model gets penalized based on the proportion of labels within each of the classes. So if there's a 100-to-1 ratio between the majority class and the minority class, this would effectively overweigh the minority class by a factor of 100. So it does that automatically just based on the nature of the imbalance. And then once we've done that, we can just retrain the model, make the predictions, and then report on the confusion matrix. And this is what we see. All right. So if you remember from the previous lecture, we had fewer true positives, so fraudulent cases that were detected, and we only had 6 false positives. So we've got far more false positives now, which is a bit on the problematic side. So we've been able to detect a lot more fraud, which is good, but at the same time, we've misclassified a lot more good customers, which is not a good thing. So what we want to do is try and balance that out. And you can take a cost-based approach, which is something that we will explore later, where these additional false positives, if you apply a cost to each of these misclassifications, the cost might be small. There might be a slight reputational cost with your customers. They might have a bad experience. There might be some operational overhead from an analyst or somebody who has to, flag this as an incorrect classification and so on. But the cost is usually quite small per unit, but it adds up if you've got 700 of them, right? Then from a fraud perspective, we've now caught, far more fraud than we did in the previous section. And fraud carries the highest cost generally in these problems. So that's the point of what we're trying to do. We're trying to detect fraud while keeping our number of false positives reasonably low. So if a cost per misclassification here would be, for example, $10, just as a simple example, the cost of missing a fraudulent transaction might be $100 or $1,000, depending on what the average fraudulent amount is within the ecosystem. Which is why it's just looking at the absolute magnitude of the misclassifications doesn't always tell you the full picture. You also want to take a cost-based approach and then see, well, maybe it's actually worthwhile if we're catching 10 more fraudsters and increasing the number of false positives, it's a possibility. It's something just to consider. And then we've plotted it out again using matplotlib and Seaborn, which looks really nice. Then as a second model to try and improve on this first one that we've created, I've introduced a more granular attempt at rebalancing the class weights. So instead of taking the default balanced approach where it just automatically, reweights it based on the proportions of each of the classes, here I've explicitly said, well, for the minority class, keep it as is, or rather for the majority class, keep it as is. But for the minority class, increase the emphasis on that class by 50, for example, which is less than if it was 100-1. So it's effectively saying, well, pay attention to that class, but not as much as you did in the case where we used the balanced value for the class weight hyperparameter. And then I can retrain the model based on that and then reproduce the confusion matrix. And you'll see in this case, we've got far fewer false positives and we've only lost out on one true positive. So from 45 fraudulent customers or transactions that we've detected, we've now dropped that to only 44. So you can see this is probably a much more, useful representation. This is a much better picture. It's more reasonable. If we're happy to lose one, but drop 700 odd false positives, I think that's a good place to be from an organizational perspective.